Okay, so here's a question. When should we use this z-interval procedure? That is, when should we use this normal curve as we just did with those numbers that were given? Well, for small samples, if we have a size less than 15, the z-intervals should be used if only if the variable under consideration is from a normally distributed or very close to normally distributed population. And we know that in advance. Plus, we also know that the standard deviation of the what the standard deviation of the population is, right? In each of these cases, the standard deviation is known. For a sample of moderate size, somewhere between 15 and 30, the Z procedure can be used unless the data contains outliers. That is, values that are much too high or too low as compared to the population. And you can certainly get that feel if you look at your data and plot it. Well, the variable under consideration also, we would not use this z if the variable under consideration is far from being normally distributed, if it's some other kind of distribution. 15 to 30 is too small, but for large samples of size 30 or more, typically the z procedure can be used without restriction. However, if the outliers are present and removal is not justified, you should compare the confidence interval to intervals obtained with and without those outliers to see what effect they have. If the effect is substantial, use a different procedure or take another sample if possible. And if outliers are present but their removal is justified and the results of the data set for which the z-interval procedure is appropriate, the procedure can be used. But as a general rule, if you're unsure whether a certain procedure in statistics can be used, go with a different procedure. Okay, so it's very simple. In the end, we say that if we're uncertain about a particular interval or uncertain about a particular distribution, well, we should be careful to make sure that we use the correct procedure. All right, let's go through an example right here. The table at right shows ages in years of 50 randomly selected people from the civilian labor force. And it's known from previous research that the standard deviation is 12.1 years. So we're going to enter this data in Excel, and we're going to determine what the margin of error is for a 95% confidence interval. We're also going to repeat the procedure for a 90% confidence interval, and then we're going to compare those confidence intervals, and we want to find out, is there a relationship between the confidence level and the accuracy of our guess, of our interval, confidence interval estimate? All right, so in Excel, I've entered in this data here, and let's go to Excel. Here it is. Our years, of course, are shown over here in column 1, and I'm going to post this data set for you guys to fool around with too on the board. Our mean, which is found by taking the average of all the elements from A2 to A51, right, all 50. Our mean is 41.38. Now, what is our population standard deviation? Well, that's given. That is 12.1 years. All right. So what we need is a 95% confidence interval. Now, here's the way this is going to work. In Excel, what we're going to do is we're going to use a confidence interval this way. It goes like this. The function that we're dealing with, shown right here, says the confidence interval from the normal distribution, we're going to give an alpha value, we're going to give the standard deviation, we're going to give the sample size. So let's go for the 95% confidence interval. Our alpha is going to be 0.05, shown here in the calculation. 95% confidence interval indicates that alpha is 1 minus 95% or 5%, 0.05. So we're going to enter it in this way. Equals confidence dot norm. That's the one we want. Our alpha level we said is 0.05. That's because we took 95% and subtracted that from 1 to get this number. Our standard deviation is given as 12.1. So we said 12.1 years. And our sample size is 50. All right, so closing that gives us our lower and upper bounds. Here they are. The lower bound being the mean, 41.38 minus 38.0261. and the upper bound being the mean 41.38 plus the MBE 3.3539. All right, not too bad. Let's try it again for the 90% confidence interval. If we have a 90% confidence interval, that means that we're going to get an alpha of 0.1. So let's try it again. Let's just see what happens. We're going to use our confidence dot norm function. And in Excel, we're going to put in the alpha number. 90% means we want an alpha of 0.1. We're going to have a standard deviation of 12.1 still. That's given, remember. And our sample size is 50. So inputting these numbers into our function gives us our upper and lower bounds this time. The lower bound being 41.38 minus 2.8147 gives us 38.5653 years. And the upper bound being 44.1947. Well, what's the effect of that? Well, if we look at what those EBMs do, certainly for the higher confidence level, we've got a much wider EBM. Take a look here. We see that 3.34 years and 2.81 years, definitely a big difference based on the confidence level. Also, we see our confidence level is 0.95, our confidence level is 0.90. We have a farther spread right here to the left and the right. Our alpha is 0.025 in each case right here, alpha over 2, right? Because we have a half of alpha to the right and a half of alpha to the left. For the 90% confidence level here shown in green, the alpha over 2 level is 0.05, so we could be 5% unconfident to the left and 5% unconfident to the right. 90% confident that our population mean age is somewhere between these numbers. So what's our relationship? Well, the confidence and accuracy are related in that for a fixed sample size, if you decrease the confidence level, you're going to decrease the margin of error. That's our MBE. And hence, you're going to improve the accuracy of the estimate. So that 90% confident interval is certainly more accurate. We're just less confident in what the numbers actually are. 95% confidence interval certainly makes it larger, right? So the relationship here is that the larger the confidence level, the larger the interval that we have to deal with, so the less accurate, right? Higher confidence means less accuracy, lower confidence means higher accuracy. There's another relationship here, and we should really talk about this. For a fixed confidence level of increasing the sample size and increasing the sample size, right? What's going to happen to our margin of error? Let's go back to Excel and just check this out for a moment. Let's say we have our confidence level, but this time let's say that our sample size was 25, not 20. All right, so what's going to happen? Well, if I decrease that sample size, we're going to put in our function confidence.norm. We're going to take our alpha for our 95% confidence interval, 0.05. We're going to take our standard deviation to still be 12.1 based on our population standard deviation that was given, but this time our sample size, let's pretend, decreases to 25. Well, we get 4.743 this time, which looks like it's a larger MBE for our 95% confidence interval, and our lower and upper levels are going to be like this. We're going to take our mean and we're going to subtract our MBE to get our lower bound, and we're going to take our mean 41.38 and we're going to add our MBE right here for the 95% confidence interval, 46.123. Well, how does this compare? Well, as you can see, if we have a smaller sample size, we get that larger interval. right? So for a fixed confidence level, if we increase the sample size, we decrease the margin of error and improve the accuracy, right? So increasing the sample size increases the accuracy, whereas decreasing the sample sizes decreases the accuracy. All right, well, that's good to know because we can use that fact if we are answering some of these questions on WebAssign. Okay, more to come.